we now look at a powerful feature of standard ML which allows us to define data types, structured data types, which are so powerful that you can represent a lot of stuff in it. Okay, so often what we have is that a type is defined by enumerating all the elements of that type. Okay, so this motivation, often types are defined by enumerating all the possible values in the type. Okay, so let's just see an example. For example, you can define the booleans as there are two possibilities, true or false. Okay. And you can construct a value of this type, some bool, by these two things are called the constructors. The true and false are called the constructors of the type. You can define them, create an object by using the constructor. Okay. Also, you can define functions via pattern matching. So we want to define the not function, for example. So let me just call this my bool, just so that just to not confuse it with a built-in boolean. You can define the not function from my bool to my bool as follows: not of x equal to something, where x is an element of my bool. Okay, we can do pattern matching here. It can be either true or it can be false. Here we can give false, here true. Okay, so this is the motivation behind defining data types of this kind. They are given by enumerating all possible values of the type. Okay, so having given the motivation, let's look at some more examples. Okay, so here is an example, the optional value. Okay, how do we capture this? So often you find that your functions might take an optional value, or it might return an optional value. For example, let's take the case of the head function. The head function, which takes a list and gives an element of that list. Okay, so you can define this as fun JD. Okay, okay, so what is the problem with this function? It's fine. You can take the head, say 1, 2, 3, and it will indeed give you a value. But if by mistake you apply this to an empty list, you will have all kinds of errors. Okay, and this error cannot be really checked at compile time, except that it can at compile time know that you have not dealt with the empty case. Okay, there is no natural way to write this function. Okay, so somehow we have to handle the empty case. Okay, in such case we can define an optional value. Okay, so let's define the optional type. Some or nothing. Okay, let's define this way. This is one of the standard types in standard ML, and we can change this to a option. Okay, head safe. Let me call this head safe, and then we have an option. If it is this, we return sum of x Okay, I can be slightly better here. And if it was empty, then we have no possible values that we can return, so we return none. Okay, so this makes sure that the empty case is properly handled. Okay, this is an example of a algebraic data type. Okay, so having seen these examples, we can now look at an example which involves recursion. Okay, so let's look at some more complicated example. So recall a list is defined by two cases: either it is empty list or it is an element followed by the rest of the list. We can capture this using a data type. If suppose, let's say that the XML language didn't support lists, we could define it this way. Nil or cons of a times, you don't need this bracket, a times a my list. Okay, so this is like saying there are two cases. My list is either nil or it is cons applied on this. Okay, and we can define functions. I mean, the embedding of this to the standard list can be defined as follows. Nil is empty and cons x is x colon okay, and is defined as empty is nil. Okay, and for example, in this setting, my 1 2 3 I can define as, let's say, rev I'll go to 3. Yeah, you can see that it is the list 1 2 3 can be captured as cons 1 comma cons 2 comma cons. Okay, so cons 1 comma cons 2 comma cons 3 comma yeah. And we can see how y looks like. Yeah. Okay. So if a list was not a default data type, we could have defined it this way. Okay. And notice that the syntax that we have here is just a sugar for this, but effectively this is the type that we are talking about. Let's take one more example. Let's look at binary trees. Again recall, a tree is defined as an empty tree, a binary tree. If T1 binary tree on A, if X is an element of type A and T1, T2 are trees of type A, then the tree with root being and T1 and T2 being subtrees is also tree. So we can model this as follows. Data type a tree equal to either it is empty, so or it is a node whose label is X, okay, node of A times a tree times a tree. Okay. Notice here that this data type is recursive, it is polymorphic, and all those things. Okay. With this definition, for example, we can define in-order traversal. Okay, in order of a tree T equal to. So this tree can either be, so we give two cases, either it is empty, so our function in order takes an A tree and gives the traversal of the tree as a list. Okay, so it can only be of this kind. Only two possibilities, let's handle those cases. So in the empty case, it's the empty list. In the case of X, T1, T2, what is it? It is in order to traverse the left subtree, which is T1. So let me call this TL and TR. Okay, so in order TL, concatenate that. Concatenation operation is given by ampersand, sorry, at the rate. Okay, X, and concatenate that with in order traversal of TR. Okay. Let's create a tree, a singleton tree. Node X okay, so let's define, let's say node of 2, 1 and 3. Yeah, let's see its in order traversal. It is 1, 2, 3 in that